So our error function would be first your input layer, that will combine into your hidden layer, this part, and then multiply it with the weight values from the hidden layer to your output layer. So wkj multiplied by this part, which takes the input values. So error function appears to be like this. So it is very complex to solve. So what can be the workaround for this? What we do is we can divide and understand into two parts. First is the case between when your W is between your output and your hidden layer, and when your W or the weight value is between your hidden layer and the input layer. So we have the weights between the output and the hidden layer for the case 1, where our input sample appears to be like this. So mathematically, it is easier to understand. It's not that difficult. So let's start with this. So what is 8nj? It is the output of the jth node in the hidden layer for given xn input. So we know that each node has a summation part and a function f part, and in this example that we will follow now, your f function or the nonlinear transformation is, we are considering a sigmoid function. Okay, so the first part is the summation. We are calling this or net, right? We are calling this summation part as net and our f function as sigmoid for the sake of simplicity and understanding. So the weights first we are going to calculate between output and the hidden layer. This is the case 1. So what about here at the node k? So first part will be or net or the summation part, and the next will be your f part or the sigmoid part. And what will be the net part? It is clear that the last layer, output layer, takes the value from the previous hidden layer. So h, this one for example would be hn1, then hn2, n1. Finally we have hnp, that are all going into your node k at the output layer. So the net part of this layer will have hn1 multiplied by the first weight over here, k1, hn2 multiplied by k2, and so forth until we have the last hidden node output np multiplied by the weight on this link. This is your net nk at this node k. So net nk is basically summation of all the output from the previous hidden nodes and multiplied by the weights for those respective links. And finally, we will do the classifier sigmoid of this net value, and the output we will obtain is onk. So the error will be estimated here. It will be the target minus the actual output, and the actual output is this. For example, our actual output is 0.8 and the target is 1. So the error is 1 minus 0.8 is 0.2. This is our error. Simple mathematics if we can write. This is our mathematics. Okay. Now we take the update of that weight value and how much new estimation, by how much weight value the new weight has to be updated so that the model is learning. For that we have to take the partial with respect to the weight value. So we can see here Net nk, we already mentioned here, it is sigmoid of n. Net nk, your onk is sigmoid of net nk. Net nk is the hidden node and the hidden values multiplied with the respective weight values, and the error function is defined by the squared error at the output layer. And what about the derivative with respect to weight value? So nth output node for n with respect to specific weight. So this output has the value from all the previous values of hidden nodes, right? And there are not only one weight value. There will be weight value here, there will be weight value here, weight value here. So for now, what we are doing is, in this example, we are calculating the error with respect to weight value w of kj. And for that, how do we define output at node n with respect to net k? Again, net k itself is a function of w weights, right? Here, net itself is a function of weight values multiplied by the hidden nodes. So if we want to calculate the error with respect to this weight, we first move to derivative with respect to partial with respect to net, and then from net we go to weight. And here we can say with net wk, we can easily select, for example, a specific weight. So only if we consider this weight value, all else will not be considered, right? So we can easily calculate our net nk, the partial. What about our error with respect to net? Net itself, for the net, we have to estimate with respect to onk, then onk with respect to net. And I mentioned this is the chain rule that we are using in our multi-layer perceptron. In the logistic regression example, I explained very clearly. So if you don't understand, I recommend that you first listen to the logistic regression lecture 3 and then come back to this slide 29. So if we take the partial of net with respect to specific weight value, simply we will get one weight value. Sorry, your h of and any value you will get, because all the other weights will not be considered. Only specific hidden node value will be considered. So this is simplified. This part is simply equal to your hidden node value, and then we have to estimate partial with respect to your output and your output with respect to your partial of onk, then from onk to net, and we have already found net with respect to w is equal to h, equivalent to your hidden node values. So now we are estimating the, focusing on this part, we have this part. So if we want to take the partial of our output with respect to the net, we can replace our onk with sigmoid of net nk, right? Here onk is equivalent to sigmoid of your net function. So we replace that here, sigmoid of net, and then we are taking the partial with respect to net. And for this part, how we come up here, I recommend going to logistic regression and slide number 11 onwards. Revisit that part to understand how we can take when we take the derivative with respect to the function, nonlinear function transformation such as sigmoid, we can get these onk 1 minus onk, and over there we estimated h of x 1 minus h of x, something like this. We already estimated that and we already discussed that. I recommend you visit that, and if it is not clear, I will discuss it again in the next lecture. So we are come up with this part, and we know this. Rest is this, the last part of our partial, which we know that it is represented in this form. From here you can see. Okay. So if we are taking with respect to specific output nk, the partial function, then what we are left is, first the partial will be reduced to this, and then we take the partial of this part. Because we are only discussing with respect to nk, it will be we will be only left with -1, which is multiplied here. So this part is equal to minus tnk minus onk. This part comes from here, and this part comes from here. So error function for specific with respect to specific weight value is defined in this format. So t is a numerical value, o is a numerical value. All these values are basically numerical values. We are not left with any partial any derivatives, and we have simplified how to estimate the back propagation, and for that we needed the partial of that error with respect to a specific weight value. So we have to update each and every weight, and for that we have to take the derivative with respect to that weight value. So here we have come up with this equation, and if we consider all the weights in the network one by one, we can write them like this. So it is represented in this format. We did this for specific weight value, but if we want to consider for all n values, error from 1, starting from 1 to n, we can use this structure, this representation of our weight update. The weights between hidden and input layer. So the next part is to estimate the back propagation from your hidden layer to input layer. From the output to your hidden layer, we have defined an equation that is easily solvable. And next we will define an equation to estimate the weights from the hidden to the input. Remember, if you need to update the weight value here, it will have an impact from the output to this node j